We'll continue to understand the challenges for TinyML. We'll still focus on the embedded systems, but shift our focus to software for embedded systems. What is software? Let me open up this box for you. Typically, what you find there is generally 3 levels of abstraction. There is a high-level application. There are the libraries that provide support for those applications, and then the operating system that provides support for the libraries and the applications. When we talk about operating systems, we're essentially abstracting away the hardware with device drivers and programmable interfaces to make it easy to program. This programming will run on any platform that supports this operating system. For a laptop, desktop, or server, by and large, we'd probably pick from one of these 3 operating systems today: Microsoft Windows, Apple Macintosh, and the Linux operating system. And if I talk about things in the smartphone side of the world, those have also consolidated into essentially these 2 operating systems, the Apple iOS and the Android operating system. Now, what's the beauty about having these widely deployed operating systems to run on most devices? Let's take the Android ecosystem, for example. An operating system and its associated parts are like the foundation of a house in my head. If you have a solid foundation, you can build the ground floor, and on top of that, you can build the first floor and the second floor, and you have a lot of flexibility in what you can do, because all of that comes down to having the right foundation, the right set of kernel drivers, the power management, and then abstracting away all of the hardware peripherals, such as the audio, Bluetooth, camera, and the sensors. And then having support for native programming languages like C++, JavaScript, and so on, so that you can actually then develop high-level applications on top of that. Now, in the context of the Android operating system, for example, here I'm showing you the platform architecture of the Android OS. Because it's got the right pieces in place, you can build high-level abstractions of libraries and stack on top of that. Why is this important? Because if you provide the right levels of abstraction, then you are able to, you enable end developers to have who are operating at the highest level, the application developers, to be able to write very interesting pieces of code, like the application that you and I have on our phones. I have almost over 100 applications on my smartphone. Each one does a specialized thing. Now, that's the beauty if you have the right general purpose operating system. This is very much true even if you look at Windows, Linux, or Mac operating systems. They have a very nice base. And then on top of that, you can build different kinds of applications, which is very interesting. Now, when you go to an embedded system, what happens? This is where I would say the world kind of all falls apart a little bit. You see, in an embedded ecosystem, there isn't really much of an operating system to say. Why? Because you take an embedded system, you typically want to specialize it to perform one specific task, like wake up when I say, okay, Google, something specialized like that. Or maybe it's designed to do health monitoring or timing. When you have something specialized like that, then you typically don't care much about having a general purpose platform. This system is built just to do this set of selected jobs or tasks and nothing else. Therefore, you don't see a lot of opportunity in terms of establishing an operating system. That's not to say embedded systems don't have operating systems. I'm giving you 2 examples here: free RTOS, or free real-time operating system, and the ARM Mbed operating system. These are operating systems, quote unquote, but typically you don't tend to have these installed. When you add an extra kind of stack on the embedded system, it actually takes away resources. Remember, we're talking about memory and compute cycles that are very small, which means that if I put an embed or an RTOS, it might very well take up a little bit of the few kilobytes of memory, and which means I have even less left over for my application. That becomes a problem, don't you think? So therefore, we don't tend to see that. And we see, if you don't see a good baseline, then building efficient systems actually becomes quite difficult, because every one of these systems is specialized. There's too much specialization, and everyone you have to roll out on your own. So let's go up one level and talk about libraries. So we know that the embedded system level, we don't have a sort of uniform, nice Windows, Linux kind of ecosystem. So what happens is when you go to the library level, well, here's a simple piece of code called np.savetheworld. NP is a library function, and it calls it 10 times. So we know it's a library function call because we say import numpy as NP. And this library is a Python library that's almost ubiquitously available on any given system. The beauty of this library is that once you write the code in Python, it can run on virtually any system, as long as it has a compiler or an interpreter for that programming language, right? And it can be an Intel processor, an AMD processor, it doesn't matter. The code just runs uniformly. You don't have to worry about it. You just focus on running your code. And then seamlessly, the code will run on any hardware. It creates this level of abstraction. So you don't need to worry about the nitty-gritty details of the lower level. And that's the beauty of a general purpose system. Now, this portability is something that we take for granted, right? We don't think about that much. But when you go over to an embedded system, this becomes a problem. Let me give you a very specific example by talking about the pi value, right? What is pi? 22 divided by 7. Very simple. Well, that translates to a very long floating point number, a number with lots of values after the decimal place. And I chose pi at 22 by 7 because it's an exciting value, nothing special. But the key point here is that we have a floating point value. Now, in a machine, a floating point value is typically expressed as 3 components here: the sign, the exponent, and the mantissa, or the fraction. Don't worry about the details. That's available in single precision format for floating point or double precision format for floating point numbers. The key thing I want to talk about here is about how floating point values is operated on. Typically, in any machine, if I have a value with decimal places, I might have 2 values, and I want to be able to add, multiply, divide, do whatever I want to do, have some general resulting value come out of that. So now I can choose to implement this function as a library, as a function call, just the way I did with np.savetheworld. And I didn't say np. And I'd say like same thing, np.multiply these 2 floating numbers. Well, that tends to be slow. So over the years, what's ended up happening is that we've gone from implementing these things as emulation mechanisms and software to actually physically implementing a floating point unit in silicon itself into the chip. And if you do this well, the chip ends up running really super fast. Well, this is actually inside the Pentium processors. For example, the Intel i486, there's a dedicated FPU, or floating point unit, that actually runs this floating point arithmetic, and therefore it can run really fast. And that's great because now, since it's proliferated, it's everywhere, and virtually every chip has a floating point unit inside it. Therefore, when you write code and these things run everywhere, then you're using that built-in floating point unit to run this multiplication of floating points very fast. But that exposes a trade-off here. If you want universal code portability across any system, you write the code once, right? Don't worry. And it'll somehow magically run on any Intel or any AMD processor. That's great. But you pay in terms of the cost. It costs money to actually physically implement it. It takes extra power, extra space in terms of transistors, because when you turn it on, it burns power because it's actually triggering the logic. And it takes a lot of engineering effort to actually build it. And sometimes these enduring efforts can be quite costly. The point is that you want uniform code portability. Well, but you're going to have to pay a price in terms of these things, right? Now I could say, forget about portability issues. It's an embedded system. I want it to be lean and mean and efficient. So I don't want to worry about general purpose portability. If you run on any of my devices, don't worry, you will run really well. But by the way, this device is going to be very cheap. It's going to consume very low power. It's going to be much simpler to engineer because that's all I've specialized it to do. I choose to vertically integrate things and shave off things that are less useful for my application type, such as if I'm building motor control or image processing or speech synthesis, I would have specific chips to do that, or power management, biometrics, or low power implantable medical devices, and so on. So microcontrollers have specialized peripherals for specific applications. But what if happens, if I want to go to another system and then to another system, then they actually, will they have a floating point capability? So assume that I start off on the right-hand side with, the checkbox where we have this wonderful FPU capability, and I write my code in my machine learning model accordingly. And then I move this over to another device and it doesn't run because I made the assumption that that processor had the capability of this floating point unit. Well, now what do? The code that I've specialized, for one system is not portable. So this raises a fundamental question that you will now need to be thinking about. How do we enable TinyML uniformly across these vastly different embedded systems if there is very low portability across these platforms? This is a critical challenge, and we'll go over how we address this issue as we step through the course. So in summary, what I'm trying to get to from the previous lesson about embedded system hardware and with this on embedded system software is embedded system hardware is extremely limited in terms of performance, power consumption, and storage. And this lesson, I'm talking about embedded software. And I said it's not as portable or as flexible as mainstream computing systems because we don't tend to have these nice operating systems. And we don't have these nice ubiquitous libraries that run arbitrarily on any given embedded device. They tend to be specialized. And we need to understand these kind of nuances as we go forward. And as we step through the course, we will be focusing on these kind of things because having this knowledge is what's going to make you a much stronger machine learning engineer, for instance, who understand what it means to deploy TinyML on hardware. And with that said, in the next lesson, I'm going to pick up on talking about machine learning challenges, specifically in the context of TinyML.